Today we're going to start talking about a huge concept in calculus called a derivative. And this is going to be with us for a while. We've got derivatives part 1, which we're starting today. We've got a derivatives part 2, and we've got an applications of derivatives. So this will be around a lot longer than limits was. So I would say, as far as relative importance, this one takes precedence over limits. However, limits are used in the development of what a derivative is, which you will see in just a few moments. So I'm going to start by telling you about an average rate of change. And the truth is you already know what an average rate of change is. I have over here on the side is just a slope of a secant line. Now a secant line is just a line that passes through 2 points on a graph. So my 2 points on the graph, I've called my points A, F of A, and B, F of B. And I've drawn this secant line. That just means it intersects that curve in 2 spots through my 2 points. And I'm going to use my average rate of change formula to find the slope of this line over here. Now, the way these points are written, it's really just an XY ordered pair. And this is an XY. This is my first one. This is my second one. So I'm really just using the slope formula. If you look at my average rate of change formula, it's F of B, which is really just y2, minus f of a, and f of a is really just y1 over b minus a, which are my 2x values. So really what this formula is in disguise is y2 minus y1 over x2 minus x1. It's just formatted a little bit differently. So let's go on and do a quick example. Example 1 is asking me to find the average rate of change of this function f of x on the interval from 2 to 3. So the first thing I'm going to do is call the beginning of my interval, that's my a, and this is my b. And now I'm just going to apply the slope formula, the average rate of change formula. So that would be f of 3 minus f of 2 over 3 minus 2. And now I have to calculate what f of 3 is, and I'm going to go off to the side and do that. So my f of 3 value is this 24, and my f of 2 value is this 6, and I'm just going to pull them into this problem, and it becomes 24 minus 6 over 1, and I get 18 is my final answer. So just some things about this. When you're asked to do an average rate of change, you always want to start with this. You want this average rate of change formula to show up in your work. So make sure that you always start at that first step. And nobody is going to be looking for you to be calculating these values. I had just done that so you could see the work. So this is the necessary part, and then you could just go straight to the answer from there. So what you need to remember about an average rate of change is it is just the slope of a line, and it requires 2 points on the line in order to use it. So now let's go on and talk about what a derivative is. And like I said, this is going to be a huge part of your life for the next couple months. So first, a little bit about notation. When you see this with a little apostrophe, that is read f prime of x, and that just means derivative. So when you see f prime of x, this just means the derivative of f. So in this graph that you see here, I have graphed a y equals f of x, that's this blue curve right here, and I've got 2 points on it, point P and point Q. And at point P, I have a tangent line right here that I've highlighted in blue. That is our tangent line. All a derivative is the slope of that tangent line. So always remember that, because that is a derivative in its most basic concept. All it really is just a slope of this tangent line, and my point of tangency is right here at that P. And so I run into some issues with trying to find the slope of this tangent line because it is just a single point. And if I'm going to use that average rate of change formula, that required me to know 2 points. So that is the root of my problem, is I only have a single point, yet I need 2. So enter point Q up here, and through point P and Q, I have a secant line. I'm going to go ahead and give names to these ordered pairs. Point P, I'm going to call X, f of X. So I go over X and up f of X. And I'm going to go out a distance from P. I'm going to call that distance H. And I'm going to define another point up here that I'm calling Q. So now when I write Q's coordinates, I went over X just to get to here, plus an additional H. So my coordinates for Q are X plus H is the X coordinate, and f of X plus H is my Y coordinate. So just one more time. To get to point Q, I go over X, that gets me in line with P, plus an additional H, so X plus H is my X coordinate. In evaluating the function at that X gives me the Y coordinate. And I have no problem finding the slope of that secant line because I have 2 points, so I would just use that slope formula to find the slope of that line. But that's not really the slope I'm after. I mean, my whole problem is I want to be able to find the slope of the tangent line. So what I'm going to do is take point Q and I'm going to move it a little bit closer to point P. I'm just going to take point Q and I'm going to move it to the left, get it a little bit closer to point P, and relocate it right here. So really all I've done is this distance H, I just made that up. All I did was I took that H and I made it just a little bit smaller so that the Q is now a little bit closer, and I'm going to draw that secant line. So now what I want you to notice is that moving Q closer to point P, it took that secant line and it made its slope a little bit closer to that slope that I'm after, that tangent line slope. But I can take point Q and I can move it even closer. So if I take that point Q and I say put it right here, so my H really only goes from here to here, and there's my new point Q. If I draw that secant line, and now we're talking about the yellow line, so now the yellow line's slope is even closer to that tangent line slope than the previous 2 lines. So the idea is I'm going to take this point Q and move it as close to P as I can. Now keep in mind, I can't get on top of P. Q cannot get on top of P, because let me show you what would happen. If Q were to land exactly on P and they were the same point, you would get a slope formula that looked like this over here. That would say f of X minus f of X over X minus X. And when you simplify that, you get that indeterminate form, that 0 over 0. But as long as I can keep Q just a little bit away from point P, as long as there's a little bit of separation and there are 2 distinct points, then I will be able to use that slope formula. So as you might have guessed, we have a limit coming on. And as Q is getting closer and closer to P, what I'm doing with this distance H is I'm closing that gap. So H is going from way over here and it's getting closer and closer and closer, so that the gap in between P and Q is getting smaller and smaller and smaller, and that H value, that X coordinate distance between P and Q, is approaching 0. Now I can't equal 0 because I can't have point Q land on top of P, but what I'm doing is moving it closer and closer. So the H, the distance between P and Q, is going to be approaching 0. So I've got a limit is H approaches 0, and all that is saying is that point Q is getting closer and closer to P. H is that distance between them. And the rest of this is just going to be my slope formula. So I'm going to do my y2, my f of x plus h, minus my f of x over the difference of my x coordinates. And it looks like this. And really all it is this y2 minus y1 over x2 minus x1. So it's just the limit as the gap between P and Q gets smaller and smaller. So Q is getting as close as possible to P without actually getting there, because once it hit 0, Q would be on top of P, and that's not allowed. And then here's Q's y-coordinate minus P's y-coordinate over, and then these are their x-coordinates. And I have a little simplification in the denominator. Those x's zero out, and what you're looking at here is what we're going to call the formal definition of a derivative. And I'm going to go ahead and write that in our third interpretation of a derivative, just to be consistent with what I have here on this side. It's called a formal definition of a derivative, is that formula that we just derived. And there it is, and we're going to be using this extensively on our examples on the back. What we're going to write in number 2 is just another interpretation of a derivative. So what you know is that your average rate of change is that slope of the secant line. Our slope of the tangent line, we often call this an instantaneous rate of change. And what that means is we are finding the rate of change at an instant as opposed to over an interval of time, which was our average rate of change. So let's do some examples on the back. So I've got a little disclaimer on the side. It's going to be very heavy in algebra, but we will learn quicker and easier ways of finding derivatives. This one is just conceptual in nature, just so that you understand that it's based on the limits. So this first question says, find the derivative, f prime of x, using the formal definition. And that is this guy. So I'm going to evaluate f of x plus h. What that means is take x plus h and plug it into my function f. So that looks like this. So my f of x plus h is all of this. And then my subtraction here is the subtraction. And then here I just write f of x. So here's my f of x. Make sure that you have the parentheses around it, because I will need to make sure to distribute that negative. And I see at this point a lot of things are going to cancel out, like my 2x minus 2x zeroes out, and my plus 5 minus 5 zeroes out. And that leaves me here. And don't forget, good limit notation has me writing the limit as h approaches 0 until I am ready to plug that h in. And notice at this moment, if I try to plug it in, I'm still in that 0 over 0 situation. But one more quick cancellation, and I can see that my answer here is simply going to be 2. So my f prime of x, my derivative of f of x, is just 2. Now, if you just think about what we just did and what you've learned about a derivative so far, we said a derivative is simply a slope. It is a slope. And if I gave you this f of x equation and I said, what is the slope of that? Every single one of you would say, hey, the slope is 2. And that is just confirmed with what we just did. And that's a little introduction to one of the shortcuts that we're going to do. But when you look at the next question, so now you have a parabola, which is a curve. So you don't have a constant slope like you did in that linear equation that we just did. So let me go ahead and do this one. You might want to go ahead and pause and try it yourself. So we're just using that formal definition. So here's my formal definition of a derivative. So I'm going to first do f of x plus h. So that means take your x plus h and plug it in for each one of these x's. And that brings me down to this step. So this part right here, the f of x plus h, here's my x plus h squared minus 4x plus h. So that's all in that red part right there. And then the minus is the minus. And then f of x is just writing the function down as is. Just make sure you put it in parentheses, because in the next step, I'm going to have to distribute. So here is everything expanded out. So my x plus h squared turns into this. So that's expanding that binomial. I'm going to take my subtraction, that -4, and distribute through the parentheses, and also this negative goes through these parentheses. And I end up with this big long algebraic expression right here. But some really cool things happen, and this will happen every time for you. The x squared minus x squared zeroes out. You've got a -4x and a +4x that zeroes out. And if you take a look at everything that's left, 2xh plus h squared minus 4h, everything that's left will always have an h in it, as you see right here. And if my remaining terms all have an h, what I'm going to do on my next step is just factor out that h. So I factor out an h, and once I factor the h, I can cancel the h's, and once I make that cancellation, I take my 0, and now I can substitute it in for the h. And when I do that, I get 2x plus 0 minus 4, which just gives me 2x minus 4. And that is my f prime of x. That is my derivative of my original function, f of x. So I want to take just a minute and talk about what that actually means. So down here, I have the graph of f of x. It's just this parabola. And what I found is that my f prime of x is 2x minus 4. So what that means, if I look at, say, x equals 2, which is right here, and I draw a tangent line at that value, so I'm just going to hit it in a single point. If I want the slope of that line, all I have to do is take my x value of 2 and plug it into my derivative. So when I plug a 2 into my derivative equation, my f prime of x, I get 2 times 2 minus 4, which is 0. So that is just saying what my graph is telling me, that if I do a tangent line at x equals 2, it's going to have a slope of 0. And you can do that at any point on the graph. So if I wanted to know the slope at, say, 4, if I wanted to do a tangent line, I could see it's a positive number, but if I wanted to know that exact slope, I would just take my x value of 4 and I would plug it into my f prime equation. And that would tell me that f prime of 4 is 4. So what that means is right here, where I drew that tangent line at x equals 4, the slope of that line is 4. And you could do that with any point, because as I pick points along this parabola, when I do tangent lines, they will all have a little different slope. And think of this thing as a formula that tells you what that slope is. So my f prime of x, think of it as just a little formula that will give the slope of the tangent line at any x you choose. Any x that you plug in, that formula will tell you what the slope of the tangent line is. As you work your way through the assignment for derivatives number 1, just realize that this is very heavy with the algebra, but as we move through the derivatives unit, we are going to learn some very cool and efficient ways of finding the derivative. So this is not your life forever, just for this one section, and it will make you appreciate the later things that we do.